Right, thanks guys. This presentation is about light interception and avocado orchard productivity. I'd just like to say at the start that most of this presentation is based on research that was done at Queensland DPI Bundaberg several years ago as part of the first Small Trees project, and in particular as a piece of work published by myself, Janine Conway, Jared Griffin and Hannah Total. Our key take-home points to start with. Avocado orchard productivity is strongly related to total light interception. If your total orchard light interception is too great and the canopy is crowding, you run the risk of declining yields. But there are approximate orchard dimensions in terms of tree height and alley width that can be used as ballpark figures to know whether you're in the correct zone or approaching the danger zone. So what is the importance of light? Well, the main importance of light, quite simply, is that when sunlight and the photosynthetically active radiation portion of sunlight hits a leaf, it allows that leaf to undergo photosynthesis, which transforms the light energy into chemical energy, which is sugar, which can be used by the tree either as the building blocks for the branches and the fruit, or actually as energy. So when we think about light interception by the tree, we can think about the leaf scale. The light does hit the individual leaves. But if we're thinking about how light interception affects yield productivity on a per hectare basis, well, the leaves on a tree shade each other, so it may not be the most useful scale to think about. Then we can think about light at the tree scale, but we know that trees in the orchard shade each other, so again, maybe it's not the most useful scale to think about. We farm at the orchard scale, so really this is the most important scale, or one of the important scales that we need to think about in terms of light interception and yield. So then we move to talking about orchard light relations. Orchard light relations are a combination of total light interception and light distribution. Total light interception is the percentage of all light that falls on an area of orchard. If we think about all the light that's falling on an area of orchard across an entire day, what is the percentage of that light that's intercepted by the tree compared with the light that just falls on the ground? We'll walk through that concept in a bit more detail in a minute, but that's the basic idea. It has been demonstrated across many tree crops over many years that total light interception is a significant driver of yield per hectare. And this is largely what we're going to be talking about today. The second component of orchard light relations is light distribution. And that's light distribution is talking about how light is shared within the canopy. Is all the light being intercepted by leaves up the top? Is there enough canopy porosity to let light filter down into the lower portions of the canopy? These are the sorts of issues that understanding light distribution helps us get a handle on. Unfortunately, I don't have much to tell you about this area of orchard light relations today. So just a bit on tools for measuring light. As Everard was talking about, we've got all this spectrum of radiation from sunlight. What the tree uses for photosynthesis is photosynthetically active radiation, which is only a small component of that spectrum, 400 to 700 nanometers. So the tools that we use to measure light are actually tools to measure photosynthetically active radiation. This is called a septometer. It's a handheld box with a bar on the end of it, which is filled with light sensors, and it's used to, this one here is actually 80 centimetres long. So you use it to measure the average of light across that 80 centimetre length. This is an individual light sensor with a long cord. So this here is the point. They're called point sensors as well. So it's measuring the light that's hitting that point. This is giving us a bit of a larger sample than this one. This one can be left somewhere, so it measures that one point, but it can measure it over a long period of time. This one is more mobile. All of these tools have their advantages and disadvantages. This is a light trolley that Queensland DBI has in Bundaberg, and what this is, along this bar, it's a collection of light sensors. So each light sensor is just measuring its individual point, but there's several of them put on the trolley, so it can measure a wide width, and because it's mobile, it can measure a large area. This combines a range of advantages. It's quite a useful tool for measuring total light interception in field trials. So thinking about measuring total light interception, we've got our avocado orchard here, 10 by 5. So the first thing we need to do when we think about measuring total light interception is understand the area that our plot, whether that be one tree or several trees, the area that our plot is allocated. So 10 by 5, each individual tree is actually allocated a 10 metre by 5 metre area. So we're not just thinking about measuring below the actual canopy. The area that tree technically allocates is its spacing, the 10 by 5. If we're measuring a 2-tree plot, which is actually what we did in the experiment that I'm about to talk about, then it's 2 lots of 10 by 5 or 100 square metres where we'll be measuring the light. It's not just the area under the canopy necessarily, it's the whole area that tree or plot is allocated. We also need to think about the position of the sun. I'm not telling you anything that you don't already know, that the amount of the way that light moves through the canopy changes during the day. So at different times during the day, the total light interception or the light interception of a tree will vary. Early in the morning, your measurements will indicate, or early in the morning or late in the afternoon when the sun's low in the sky, your measurements will indicate that the tree is intercepting a large amount of light. When the sun's high in the sky at midday, your measurements are probably indicating that the tree is intercepting less light. So what we need to do to get that integration of light across the entire day is maybe we measure multiple times during the day, or maybe we wait until we've got a cloudy day and we just measure once during the day. Because with a cloudy day, the light being scattered, it's almost as if you've got light coming from every direction. So one way you can measure total light interception is get your septometer, and for our 2-tree plot here, you can use a grid-like pattern to go into great detail and cover all of the area that your plot occupies. And in this example, we've got a 10 metre width going from halfway between one row to halfway between the other, and then the length along the row that the plot occupies, and we can run a grid section. We could do that early in the morning, mid-morning, noon, to get an average, or we could wait for that cloudy day and just measure it once during the day. The other thing that we need to do is to compare these are called below canopy measurements. we need to compare them to an above canopy measurement, light measurement, so we've got the percentage of light that's making it down to the ground. From that, we can work out a percentage total light interception. So I'll now move on to talk about our avocado baseline light interception study, which we did in Bundaberg about 10 years ago. So the purpose of this was, as I said, across a range of tree crops over many years, total light interception has been demonstrated to be a strong driver of yield. We wanted to investigate these relationships for avocado. It was a relatively simple thing that had just never been done for avocado. So what we did was, in Childers, we tried to compress the experimental material into as small a zone as possible, because we know how environment and management can impact yield. So we worked with Simpson Farms and did the vast majority of this work on their orchard. We couldn't quite get all the plots that we were after, so we went across the road and did a few plots in their neighbour, so different management but basically the same environment. We did all this to minimise the error of environment and management. So we chose orchard blocks from soon after planting up to mature orchard blocks. We were trying to get a range of tree sizes. Over 2 cropping seasons, we measured canopy size, total light interception and yield for 3 plots in each of these 12 orchard blocks. So we had 36 data points every year. The light interception was undertaken once for each plot each year in diffuse light conditions, so cloudy day in other words, and we only had to do the measurements once per day. We used a septometer with an external sensor above the canopy so that we could work out a percentage, and we did it across that entire area that our plot occupied, not just under the actual canopy, done on hats. So these are some of the results. This is the relationship between canopy volume in canopy volume per hectare, so not just the tree, calculated up to be per hectare, against the proportion of total light intercepted. So apologies, it's a proportion, it's not a percentage, but 0.2 is 20%, 1 is 100% light interception. These are the results for the 2 years. Slightly different relationships depending on the year, but same in essence. So what we find is, just above 0 canopy volume, so a very small tree, soon after planting. As we increase canopy volume from low canopy volumes, we're getting a very strong increase in the amount of light intercepted. It's not linear, there's still a curve, but it's for each cubic metre of canopy volume we're increasing, we're getting also a high increase in the percentage of light that's intercepted. As we get to higher and higher levels of canopy volume, the amount that the increase in total light interception we get as we increase that canopy volume gets less. Our curve begins to flatten to the point where when we go from 30,000 cubic metres of canopy volume to 40,000 cubic metres of canopy volume, we're only increasing our total light interception by maybe 5%. When we go from 0 to 10,000, we increase about 30% total light interception. What this means, we didn't measure it, but what happens is the larger the individual canopies get, the more they shade, the more it shades itself. The more leaves you have, the more they shade each other. Most likely what is happening is that in these very large canopies, we're getting quite a large proportion of those that have got low light in them. The shape of this relationship was expected. It's similar to other tree crops. Now we'll go to looking at the relationship between canopy volume per hectare to yield in tonnes per hectare. Again, large parts of this curve were not unexpected. We've got 2 years here, 2015 and 2016. What we had to do was fit 2 curves. Neither curve we were particularly happy that it was explaining it better, or explaining the relationship better. In any case, as we go from low canopy volumes per hectare and increase, so after planting, as the canopy volume increases over the first years, we also get a strong increase in yield per hectare. I'm sure I'm not telling you anything you don't already know there. Until we get to around about 30,000 cubic metres of canopy volume, maybe a little less, and we start to reach a plateau in yield. Well, one curve is indicating a plateau in yield, another is indicating a peak. But in both 2015 and 2016, it was approximately at the same point, around about that 30,000 cubic metres of canopy volume. Then we were unsure. One of the curves indicates that there is a decline in yield after you get above 30,000 cubic metres of canopy volume. The other curve is indicating that the plateau continues. For those who are interested in the stats of it, the declining curve here explains 0.77% of the variation. Down here it explains 0.82. Up here the plateauing curve explains 0.78 of the variation, and 0.79 down here. There's not a huge amount in it. Now we can look at the relationship between total light interception and yield per hectare. Again, it's as a proportion, but yeah, 1 is 100%, 0 is 0. Again, nothing surprising that as we move from low levels of total light interception and increase, our yield is increasing strongly. Up to a point at around about 80% total light interception. When we're around about 80% total light interception, we're reaching our maximum yield. Once again, it may be that the relationship plateaus, or that as we move above 80% total light interception, we get a decline in yield. Once again, we didn't feel we were able to confidently say that we either continued to plateau or we got a decline in yield after we moved above the 80% light interception. One thing that we were able to do from the work was to look at plots within our data set which were low, medium, potentially optimum and potentially too large, and pull out the actual canopy dimensions that represented those approximate total light interceptions. So small canopy, 22% light interception, 3,500 cubic metres per hectare. It's a canopy height of about 3.4 metres and a canopy width of about 3.3 metres. Moving up to 80% total light interception, canopy volume about 30,000 cubic metres per hectare, canopy height about 8 metres, maybe a little more, canopy width about 8 metres. I should mention here that these orchard blocks were either 10-metre row spacings or 11-metre row spacings, indicating that we've got a 2 to 3 metre alleyway here. 89% total light interception, maybe moving into a danger zone, maybe not, depending on the curve. A little less than 40,000 cubic metres of canopy. Canopy height, almost 9 metres. Canopy width, almost 10 metres, which is indicating very little alleyway, or none at all, or basically none at all. So, you know, about the 80%, which is about optimum top of the plateau or potentially optimum yield, maximum yield, canopy height a bit over 8 metres and a 2 to 3 metre alleyway. Potentially the danger zone, closer to 9 metre tree height, little to no alleyway. So the main conclusions that we can get from this, as expected, light interception increases with canopy volume, although smaller increases in light interception with canopy volume as the orchard begins to crowd. This is indicating mutual shading within the tree and probably greater proportions of the canopy with low light levels as it's beginning to crowd. Yield increases with total light interception up to about 80%, and we can't conclusively say whether yield plateaus as the canopy gets larger and we get to larger levels of total light interception, or whether you do get a decline. But I think it's fair to say that caution should be exercised allowing your canopy to get above 80 to 85% total light interception. This was undertaken on Hass, unknown what the relationships will be for Shepherd. Going back to our key take-home points, avocado orchard productivity is strongly related to total light interception. If your total orchard light interception is too great, you do run the risk of yield decline. And we showed you those approximate orchard dimensions to know whether you're in the optimum zone or potentially the danger zone. I've got that next project. Do you want me to see if I've got questions now or just talk about that next project now? Talk about the next project. Okay, that was our piece of work about total light interception and productivity. I just thought I'd take the opportunity to introduce a new project which has only just started. It is called Optimising Avocado Yield with Region-Specific Canopy Management, Insights from Light Interception and Canopy Modelling. So the project goals here, or the purpose of the project, it's essentially a scoping study, a 12-month scoping study to understand what work has been done on canopy management, understand industry needs, understand technology available, and make recommendations for what should be included in a full canopy management, long-term canopy management project. So this is just a scoping study to understand what has been done, what people need, and what work should be done. The project team, it's been led by Gerhard Grosso from Queensland DPI. He's based in Mareeba. I'm part of the project team, and also Neil White from Queensland DPI in Toowoomba. He's a modelling expert. Yeah, it's a one-year project. What are we going to do? First of all, we're going to review literature on avocado canopy management and orchard physiology, in particular orchard light relations, related physiology. We're also going to review literature on orchard light modelling options and sensing technologies for application for R&D or for commercial applications. We're going to talk to growers in a range of growing regions to try and determine what growers think they need in a canopy management study, in terms of canopy management strategies. We will go to Far North Queensland, Central Queensland, New South Wales, Western Australia. We're also going to talk to modelling experts, sensing technology experts, and commercial tech providers to understand what potential options are, again, for R&D or for commercial application. And then we'll make recommendations in terms of what should be included in the R&D project, in the full canopy management R&D project.